morning all. In this lecture, a series RL circuit is explained. Here in this circuit, you can see that a resistance is connected in series with a pure inductor and the combination is connected across a voltage source Vt. The voltage source is assumed to be sinusoidal. And when the circuit is closed, you can see that a current will be flowing through this series combination. And you can see that being a series circuit, the same current will be flowing through R and L. And here you can, as we have seen in the previous lectures, the current through a resistance and the voltage across the resistance will be in phase. That means there won't be any phase difference between the voltage through a resistance and the voltage across the resistor. But in case of a pure inductor, the current through the inductor will be lagging with respect to the voltage across the inductor by an angle of 90 degree or pi by 2 radians. Here, being a series circuit, for the analysis purpose, we are considering the direction of the current through the inductor or the current through the circuit as a reference. For the phasor analysis, we will be considering the current phasor as a reference. So, this is the reference direction, which is the direction of the current through the circuit. And here you can see that when a current flow through a resistance R, the drop across that will be given by the product of the current through the resistor and the resistance value. So the drop across the resistance will be given by VR is equal to I into R. And you can see that there won't be or there will not be any phase difference between the drop across the resistance and the current through the resistance, because I is flowing through the resistor R and the drop across the resistor is VR, and there is no phase difference. That is why we have drawn VR along the same direction as that of the current through the resistor. But now the drop across the inductor is given by the RMS value of the RMS value of the drop across the inductor is given by the RMS value of the current into the inductive reactance XL. And you can see that the voltage across the inductor will be leading with respect to current through the inductor by an angle 90 degree. So this is the reference direction and this is the phasor representing the drop across the inductor, which is given by VL. The phase difference between the drop across the inductor VL and I is 90 degree, and here voltage phasor is leading with respect to the current phasor by an angle 90 degree. Now you can see that the drop across the resistor plus the drop across the inductor will give the total applied voltage, and all these quantities are represented in phasor form. So this is the phasor representation of the applied voltage. You can see that if you add this vector and this vector, the resultant will be this vector. And if you apply Kirchhoff's voltage law to this law, the sum of the drop across the resistor plus the drop across the inductor should give the applied or the total voltage. So in phasor form, the drop across the resistor plus the drop across the inductor will give the total applied voltage. But the only difference is that here all the drops are to be considered as phasors, and all these two drops VR and VL are to be added vectorial. And if you here we have taken the direction of the current as a reference. So the current signal or the current waveform can be represented as Im sin omega t, because we are taking current as a reference. So if you are considering a particular phasor as reference, it will be represented as magnitude, its magnitude, that is magnitude of I angle 0 degree, because it is drawn along the reference direction. And here we can see that the drop across the inductor, it is leading by an angle 90 degree. So it is represented as IXL, which is the magnitude of the drop, and this is the angle it is making with respect to the reference direction, and it is leading by an angle 90 degree. So VL is written as this is the magnitude, this is the angle, and it is equal to as we have seen in the previous lectures, angle 90 is equivalent to J and XL is obtained by omega L. So this can be represented in Cartesian form as J omega L into I, and you can see that the drop across the resistance is IR angle 0 degree, so it will be I into R. From here you can see that if you consider the direction of the current as reference, the total applied voltage or applied voltage is leading with respect to the current phasor by an angle 5 degrees, which is less than 90 degree. So the phasor V can be represented as magnitude of V or the RMS value of V angle 5, and you can see that this is plus 5, this leading with respect to the current by an angle 5 degrees. And in that case, if you consider this as the reference signal, IT is equal to Im sin omega t, this is the voltage signal which is leading by an angle 5 with respect to the reference. So Vt can be written as Vm, which is the maximum value of the voltage signal, sin omega t plus 5. Now, if you consider the phasor diagram here and if you scale it out or if you divide all these magnitudes by I, you get this triangle. Here you can see that this magnitude divided by I will give you Z, here it will be XL and here it will be R. That is how we are getting this phasor diagram or the impedance triangle. Here you can see that from here V is equal to VR plus VL, that we have already explained. It is VR is equal to RI and VL is given by JXL. If you combine these two, you get R plus JXL into I is equal to IZ. Because here we are considering R plus JXL as Z, which is known as the impedance of the circuit. So impedance of the circuit is given by, in Cartesian form, it is R plus JXL form, which is where R is the real component and XL is the imaginary component. And in phasor form, it is, or in polar form, it is magnitude Z angle 5. And the relation between the magnitude Z and R and XL can be obtained from here. Here you can see that if you consider the projection of Z along the direction of I, it will be Z into cos phi. And here you can see that it will be equal to R. So we get this relation, R is equal to Z cos phi. And here, if you take the projection of Z along the vertical axis, it will be Z sin phi, and here it is equal to XL. That means, which give a relation XL equal to Z sin phi. And from this impedance triangle, you can see that magnitude or the magnitude of Z is given by square root of R square plus XL square. That is this relation. Z is equal to root of R square plus XL square. And tan phi is equal to XL divided by R. From we obtain a relation phi is equal to tan inverse of omega L by R. Now you examine the variation of the voltage, current and power waveforms. These are the variations. Here you can see that here in this case we have taken the current as reference. So it is represented as IT is equal to Im sin omega t, and the voltage is leading with respect to the current by an angle phi. So voltage is represented as Vm sin omega t plus phi. Now if you see the variation of the voltage and current waveforms, here you can see that we have taken I as reference. That is why we have started the waveform I from origin. So this is the reference, and you can see that the voltage waveform is leading with respect to the current waveform by an angle phi, which is less than pi by 2 radians. Now if you shift the origin from this point to this point, you will get this waveform. Same waveforms are there, and additionally we have plotted the variation of the power also here. So here you can see that now instead of this point, here is the origin. So the voltage, you can consider voltage as the reference waveform. So it is starting from the origin, and you can see that the current is lagging with respect to the voltage by an angle phi. Now if you plot the variation of the power, here you can see that the voltage is positive here and the current is negative. So during this period power will be negative, and from here to here you can see that voltage is positive, current is also positive. So power is positive here, and during this period you can see that voltage has changed its sign, so it is negative, and the current is still positive, but the product will be negative. And this region, or during this period, you can see that both voltage and current waveform have negative values, so the power will be positive. Now if you consider the total power over a complete cycle, this is one complete cycle, and you can see that the positive power or positive area is higher than the negative area. So if you sum up all the areas, positive and negative of the power variation, you can see that the total sum will be always positive, because this negative area are magnitude wise less than that of these positive areas. So as a whole, during one complete cycle, the total power consumed by the circuit will be positive. It can be from the waveform we have seen in the previous slide. V can be represented as, or if we are considering voltage phasor or voltage signal as reference, V can be written as V is equal to Vm sin omega t, and current in that case it will be lagging with respect to the voltage waveform by an angle of 5 degrees. So it will be represented as I is equal to Im sin omega t minus 5. So power can be represented as P is equal to Vm sin omega t into Im sin omega t minus 5, which is obtained from this relation. P is equal to Vi. Instantaneous power is obtained by the product of the instantaneous value of the voltage and the instantaneous value of current. And here it can be written as Vm Im by 2. We have divided and multiplied it by the expression by 2. So this can be written as Vm by root 2 and Im by root 2, which is the RMS value of the voltage and the RMS value of the current. And 2 sin omega t minus 5 into sin omega t can be splitted like this. It will be cos phi minus cos 2 omega t minus 5. So it can be written as P is equal to Vm by root 2, Im by root 2, which are the RMS values, into cos phi minus this expression. Now if you find the average value of this whole expression over a complete cycle, that means if you integrate the whole expression from 0 to 2 pi and divide by 2 pi, that means 1 by 2 pi integrate from 0 to 2 pi of this whole expression with respect to d omega t. Here you can see that with respect to d omega t, this is constant. So the average value of this part will always be Vm by root 2 into Im by root 2 into cos phi, which is given by this. And the average value of this, or the integral of this portion, integral from 0 to 2 pi Vm by root 2 Im by root 2 cos 2 omega t minus pi d omega t. We are integrating with respect to omega t. This expression will be yielding a result 0. So the average power will be equal to P is equal to Vm by root 2 into Im by root 2 cos phi minus 0, which will be equal to Vm by root 2 into Im by root 2 cos phi. So it can be written as Vrms into Irms into cos phi. This term is known as the power factor of the circuit. Cos phi is known as the power factor of the circuit, and the term V into I is known as the apparent power, and real power is obtained by V into I into cos phi, where V and I are the RMS value of the voltage and current phases. So, and cos phi is known as the power factor of the circuit, which is defined, or which can be obtained from this relation also. Cos phi is equal, because VR is obtained by VR is given by capital V into cos phi. So here it can be substituted by IR, and here it can be substituted by IZ. So you get power factor cos phi is equal to R by Z. Now if you substitute for V and I and cos phi from these relations, you get P is equal to IZ into I into R by Z, which is equal to I square into R. You can see that the power consumed in a RL circuit is dissipated as heat in the resistor, which is given by I square R. If I is the current flowing through the resistance R, the power dissipated is given by I square R. So all the power dissipated in the series RL circuit is dissipated as heat in the resistor. Thank you for listening.